All right, then we will go. Hello, my name is David. I'm a co-founder of Orella Vision, and the last 9 years I was working in the field of visual AI at the edge. I was working within product development and with project work. So today I want to talk a bit, give you an overview of what I learned in these years about important parts here and lessons I learned and we learned at Orella Vision. So let's go. So nowadays, creating impressive demos, I have the impression becomes more easy, especially because there are so powerful frameworks, some, like Autolytics or RoboFlow, which just requires a couple of clicks or one line of code to train a model. There are tons of open data sets out there. And then you can use some vibe coding to just make an app shell around it. So you're very quickly in prototyping some very quick demo. But when you want to move then to a real system operating in the real world, there's usually a quite far way to go. That's mainly because the reality forces some boundary conditions onto you. So what you will face usually is you have to place your system somewhere in the real world. Sometimes it's outside. Sometimes your edge system is on a moving vehicle, like the camera as well. All of this will expose you to camera movement, vibrations with this motion blur, limited energy available, then rainy conditions, all of this, all of these circumstances. Another thing which is also very important in my opinion to address here is that a successful solution is not just the ML model alone. I say this because ML models, deep neural networks and so on, they get a lot of attention, right? But they are really very much embedded in the software and they are one part. So in a vision pipeline, they are just one element. And again, this vision pipeline is part of another software which takes care about, updates, the setting system and whatnot. And this software is running on your edge hardware then. So you see there are a lot of topics here. Today, due to the time box as well, I want to talk about my favorite topic in this domain, which is the machine vision pipeline. All right, if you look at such a type pipeline, we have usually the following blocks. So we have a camera block. This here represents anything which gives you image data. Then you have a pre-processing block, which prepares the data coming from the camera to suit optimally the model. Then you have the model, well, most of the time some kind of ML model, which does the perception part. So it classifies something, it detects something, it makes segmentation. And after this, you have a post-processing step, which uses this output. So it smooths label, it utilizes maybe the time domain, it assigns IDs, it tracks objects. Then there is the decision block, which actually now bridges these outputs of your pipeline with the value of the user, right? This is the block which then triggers alarms. It's the block which makes database entries and so on. As a last block, there's a integration layer. So maybe you have a dashboard you want to integrate in your customer's existing infrastructure or something like that. All right, so a machine vision pipeline has to work with cameras. Maybe some important points here. In a project, it's sometimes you have the possibility to choose the camera. Then you're lucky. In other projects, it's already part of the infrastructure, right? Nevertheless, a camera has optics and it has a sensor, and they define the characteristics. So now I think practically it makes sense to think about what does your perception system need. So what do you want to solve? Maybe you want to detect something in a specific distance. You want to do identification in, I don't know, 100 meters. This will determine a specific pixel density, which then can be translated into optical and sensor requirements. If you, on the other way, are already confronted with the infrastructure, you can still wrap your head around this, because calculating what is possible on the perception block very early will make a discussion with your customer with potentials yeah, much easier. I added here a resource. I think it should be possible to share the slide somehow afterwards with you. A link to research for yeah, a calculator bridging this field of view sensor resolution with perception capabilities. Maybe very shortly, cameras can be calibrated. You can understand the intrinsic parameters and the extrinsic parameters. So intrinsic parameters somehow just describe the lens model. The extrinsic parameter describe where is the camera in respect to another coordinate system. So like maybe the camera on your vacuum cleaner robot knows where it is in respect to the base station. Maybe here, quick guide, when would you need to use calibration? I would say when you're in a robotic or in a navigation environment, you definitely need calibration, because you have to relate each point in the image with a real point in the real world. When it's just about monitoring and you just want to say there's something in the image, you don't need calibration. All right, pre-processing. Well, the first thing you have to do, you have to decode the stream, right, coming from the camera. I think the most important thing here to say, nowadays, edge platforms, all I know, have some kind of hardware decoder part. Please use it, because otherwise it will eat up so much of your CPU. I linked also resources here, helping you to choose the right one. Then denoising, it's for sure an interesting part as well, especially if you work with sensors who are price effective or just cheap. Their signal to noise ratio can be bad, especially if you have low light conditions. You want to improve your image, then or denoise your image as best as possible. This will also improve downstream your performance. Very interesting as well. Okay, this video is not running. I don't know why. Well, very interesting as well is when you're when you're on a moving platform, you will have to deal with vibrations, and you want to get rid of them. The reason is your tracking system down the line will have a hard job correcting for this. So you can introduce a pre-processing step which stabilizes those videos. So usually this is two-folded. In the first step, you find a correction factor from the first or from consecutive frames. This can either be done by tracking some features, or it can be done in a dense mode via the frequency domain. So I listed a few methods here. I think we don't have enough time to go in detail. Then as a second step, you have to estimate the motion of the camera. Why? Because if you just apply the displacement, your image will go away and you integrate up an error. So yeah, here you can do either a simple Kalman filter or a high-pass filter, for instance. There are different methods. All right, then image undistortion. if you understand you already did some camera calibration, you can undistort the image. That can be very important as well in some situations to improve your model perception performance. Especially if you do this on a high resolution, it can be very demanding for your platform. So make sure again that you use all the hardware acceleration possibilities. You can find here, I linked again some resources. So you can refer to either OpenCV and CUDA accelerations here. I also have a DeepStream resource linked. Additionally, color space correction or color space conversion can be very interesting, but you should look at this during the training process already, because just training on RGB might not be the best for your specific use case, for your specific domain. It can be that another color model makes your model perform better. Now, just a simple example, if you're convinced that the most information in your data lies within the texture and not so much in the color, then you can transfer or make a conversion to grayscale, skip the two channels, just have one channel, have a faster model, and reach the same performance. All right, then you train it's about the ML model. Well, a model alone, even if it's a great architecture, doesn't perform if the data is not also good. So let's quickly have a look at data and data sets. Yeah, within a project, I think at a very early stage, you should try to get data from your customer, of course. If you're lucky and like they already have some data because maybe it's a CCTV, they have some CCTV footage, whatever it can share with you, that's the optimal case. Otherwise, you have to wrap your head around and talk with the customer how you can retrieve this on-site data. Another thing which also makes a lot of sense is to find similar data to your domain. Of course, that's online, like you can go on Kaggle or Overflow. You can go to research data sets. Just make sure to check the license. Yeah, if you find something, will be very much dependent on how exotic your specific use case is. Something getting more popular nowadays is synthetic data, especially when it's about navigation. Simulated data is very great. Okay, so what used to or what works very well for us usually is when we have a new data set, the first step is we want to explore it and we want to clean it. Yeah, here we love to use 51 for visualizing our embedding space. That means like we run all our data through a powerful model, maybe Dino 3 or something, to calculate robust embeddings. Then we project them to a 2D space using, yeah, there are different methods like Disney, UMAP, which will show us then the relation of the images to each other. This helps us to remove duplicates or near duplicates and maximize the variety within our data set. Additionally, when you already have a labeled data set, it helps you to track down labeling mistakes. Labeling of data is another huge topic. Well, you can refer to tools like CVAT, Label Studio. You just can go to RoboFlow as well. There are many different possibilities, or you can outsource this. Yes, well, going in detail here is too much. Maybe one thing which also it's easy to check and you shouldn't forget is to look at your label distribution and don't let it to get too much unequalized. Yeah. All right, the ML model. Well, if it's about edge computing, out of the available models, you're already dealing with quite a subset, which is potentially runnable on your specific platform, right? One advice might be don't try to start to use, create your own model. There's a huge world of powerful models out there. Try to use one of those. Many of the state-of-the-art models, they already have benchmarks how fast they will run on your edge platform. So look this up and decide for small subsets of models that usually worked for us. And another thing you might want to take into account is if you can find pre-trained checkpoints you're allowed to use, which were trained on a data set similar to your project data. If you have something like that, that will kickstart your training. Now, during the training process, if you use a powerful framework like maybe Autolytic and you just go for a YOLO model, you have one line to start the training. I think it still makes sense to roll up the hyperparameters and the augmentation and have a look if the standard settings apply or are meaningful for your specific domain. For instance, a classic is the rotation augmentation, which makes sense to have it 360 degrees, when you're in a bird view perspective, or maybe you analyze medical images, but it doesn't make sense for a camera which has always the same upright position. Yes, then what, I don't know, I always find useful. So when you create your own training pipeline, you make some changes, you adapt loss function or whatever. Don't go for a full train run right away. Use a subset of your train set just to see if conversion, everything is still as expected, because you don't want to wait 2 days just to notice that you did a stupid mistake. What also, in my opinion, is important, documenting and experiment tracking from the first experiments is also very important, because very soon you lose oversight otherwise. There are great tools out there, from weight and bias to MLflow, some of self-hosting, some online. Now about deployment. A typical deployment route goes like this. You have your training framework like PyTorch or TensorFlow. You go to the ONNX format, and from there you convert to your target platform runtimes. You do this with tools usually provided by your target platform provider. I don't want to talk so much on hardware here, so just for you to watch out when you select an edge platform is the TOPS, the RAM, and the memory bandwidth are dominant in parameters which determine how fast your model runs. And another thing is, once you already work with a specific platform, like for instance NVIDIA with DeepStream, you may already have a lock-in factor in the ecosystem because you already invested time there to build some elements, some libraries that might be also influential. Okay, you want to make the best possible model run on your platform. So you want to search for methods to accelerate it as much as possible for the highest performance. There are techniques like quantization. I think the fastest route for results is to start with post-training quantization. The reason is you don't have to touch your own training loop. You can directly refer to tools of your runtime provider. The first step, maybe what you do is to go to float 16 quantization. This usually comes without accuracy loss or very little. Most modern edge platforms also support int8. Currently, doing this will give a huge speed up, but you have to be careful not to lose too much accuracy. Therefore, usually you have to provide during the transition process subset of your training data. It's like maybe 100 to 500 images, and you give it to the translation tool from ONNX to your runtime format. Quantization-aware training, well, that's a technique which promises even better accuracy, but it's more complicated. I don't want to go into detail right now. The same with pruning. If you look into pruning, look into structured pruning first, because that can be utilized much easier in a speed up, but it's not so easy to do. So that should be rather on a further step of optimization. Yeah, you can look into torch pruning. It's a great framework, but yeah, you can contact me if you want to know more about this. All right. Yeah, it's a bummer that the video is not working. Okay, well, I will just verbally say post-processing. Well, your model did all the perception task. Now, what you want to do usually is you want to use the time domain as good as possible as well, right? If you're having a classification task, maybe you want to smooth the label. If it's more on a task of detection or instance segmentation, you want to track this individual instances. So you have a multi-object tracker behind. You want to assign these instances an ID. And what you can also do is you can see how robust are those, because something which is just maybe detected once is not very robust and can be filtered out at this step. This can boost overall performance of your system. Also, tracking allows you to get to estimate dynamic behavior of your things you track. So for instance, if you have cars and you track them, you can estimate their velocity, where they're going, so their trajectory. And famous trackers here, ByteTrack works great. When you work with NVIDIA, they have a great NVTrack library built into DeepStream. It's they have pre-implementations of powerful tracking algorithm accelerated on their hardware. So have a look at this. It's great. The situation gets a bit more complex once your camera system moves as well, because then not only the object in the scene moves, but also your camera. It might be necessary there that you adapt most or available trackers here to your specific movement. I think something important mentioning at this point is that your system performance will be judged on not only the model alone, but also on the post-processing, right? On the tracker or whatever comes after this. So it makes sense to tune the whole system end to end. So run through your validation set and tune the parameters. Usually you would have a tendency to reduce your confidence threshold a bit, because the tracker can usually handle a few false positives, but it will make your system a bit more sensitive. I think at this point it also makes sense to think about if you're willing to have some false positives in your overall system, therefore have a very good very high rate in detecting, or the other way around, that you say like it's okay to have a miss once in a while, but you don't want to have any false positives. I think that's very much application dependent, but I think you should be aware during the tuning process what you are aiming for. All right, so this is, I think, personal learnings I had to do as an engineer in this in the industry. I think maybe some people relate to this. So as an engineer, I'm naturally in love with the technology. with the possibilities, but working on a project requires you to keep the problem in the center. So obsess rather over the problem. So especially if you work in a new project and and there are some insecurities inside, you don't know exactly the solution right away. Step back. Don't be shy to introduce a pilot phase and try really to evaluate edge cases. Where does the system have to work? Where are the limits? Contact your customer here. What's necessary? And just after this, try out different technologies and deep dive in the technology of your choice just after this. It will eventually save you a lot of time. And my second key learning I made over the years is, especially coming from academia, is that robustness is very often more important than big accuracy. I say this out of this context than when I was still in university. I wanted to show that the algorithms perform as best as possible, and you can usually control the boundary condition yourself. You choose a data set, and you can choose the platform and the model on your own, right? So you don't have so many constraints. While on the other side, in a real product, the environment will give you these conditions. It will say like it has to work outside, it has to work in different conditions. It can be rain, can be snow, fog, and so on. And you have to perform in all of this. And if it's not possible to perform in a certain condition, then at least your system has to be aware of this. Yeah, say that were the most important learnings I want to talk about right now. All right, yeah, we're at the end already. So we at Orella Vision, we make consulting and engineering services around edge products. So if you need some help on your edge development, then let us know. Contact me or us via my email address or go on our homepage. You can also find me on LinkedIn. And thank you for your attention.